Hello everyone, welcome back. In this particular video, we're going to start talking about the crossed aldol reaction. Now, this is also called a mixed aldol reaction, and this is where we get into some of the technicalities of the aldol reactions and some of the issues that we might face while we are carrying out an aldol reaction, and how do we circumvent those problems or those issues to get practically useful aldol condensations or aldol addition reactions. So let's look at an example here. And with the crossed aldol, we're looking at the reaction between two different carbonyl compounds. Okay, so let's assume we have two ketones for the discussion here. We're going to assume that we have two ketones. Now, it does not have to be two ketones. We can also look at a scenario where we have two aldehydes, or we have an aldehyde and a ketone. So all of these are possible scenarios, but we are working with two different carbonyl compounds. And for the purpose of the discussion, I'm using compounds that both have alpha hydrogens. Okay, so the first carbonyl compound that has alpha hydrogens on it, and the second carbonyl compound that also has alpha hydrogens in it. So when we do an aldol reaction using two different carbonyl compounds, what you can imagine is that, and if we use basic conditions for our purposes here, the situation is not very different when you do it under acidic conditions. So under basic conditions here, we can see that we will make two enolates here. Okay, there are two possible enolates that can be formed. We can get an enolate from the first carbonyl compound. So we're going to have one enolate that's going to be this species. Okay, that's the enolate from the first carbonyl compound. And we're going to have an enolate from the second carbonyl compound under these conditions, because the base can deprotonate either one of these compounds. In fact, both of the carbonyl compounds here, okay, not either one. The base can deprotonate both of them. And so we'll have two possible enolates here. Now, once this enolate is formed, which is the enolate from the first compound, okay, the enolate, we'll call it enolate 1, and we have enolate 2. Okay, once these enolates are formed, they can react with both of these carbonyl compounds because they're not going to differentiate between them. So in principle, enolate 1 can react with the first carbonyl compound, and it can react with the second carbonyl compound. Okay, so it can react with, both carbonyl compounds here, not aldehydes, just ketones. So the enolate 1 can react with both of these carbonyl compounds. And so if it reacts with itself, okay, or it reacts with one of the carbonyl compounds that gave rise to this enolate, then we're going to get beta hydroxy carbonyl compound, which is going to look like that. And there will be a methyl group here. Or if it reacts with 2, then we'll get a beta hydroxy carbonyl compound. That's going to be this compound here. Okay, so we'll get two different beta hydroxy compounds from this first enolate. Now, the same situation is going to happen with the second enolate, because the second enolate, again, it can react with the first carbonyl compound, or it can react with the second carbonyl compound. So that means we'll get R2 carbonyl compound, hydroxy, R1 methyl group, and we will get R2 carbonyl compound, hydroxy, R2, and methyl group. Okay, so what you notice here is under this scenario, or in such a situation, In principle, we are going to have 4 products. And if we do this reaction with heating, or if there's like a slightly forcing conditions, then all 4 of these products can in principle convert to their corresponding alpha beta unsaturated ketones or carbonyl compounds. Okay, so we have 4 products. So this is not good because we are doing a reaction and what we're getting is a mixture of 4 products. And so if we want one of these products, what we would have to do is we will have to then do some separation, like chromatography or crystallization, whatever that might be. Okay, whatever would work, we'll have to do some separation to get the desired product or to separate them out, like all 4 of them out. Okay, so that's really not ideal. So for practical purposes, or to make this reaction more practical, okay, what we do is we choose this reaction is done by using only one carbonyl compound. Okay, only one of the carbonyl compounds has alpha hydrogens in it. That means there's only one carbonyl compound that is capable of forming the enolate, right? So if we have 2 compounds and out of those, one is only able to form the enolate, then we eliminate one of the enolates. So now we are looking at a situation like this. Let's say we have R1, C double bond O with alpha hydrogens. This has alpha hydrogens. But the second compound, the carbonyl compound, is R2, C double bond O, R2, let's say. And we'll say that this has no alpha hydrogens. There are no alpha hydrogens in that compound, which means when you react it with a base, when you react this mixture with a base, you're going to create only one enolate. Okay, so this will give you one enolate. That's going to be this enolate. There's only one enolate formed. Okay, but now once this enolate is formed under these conditions, this enolate can react with both carbonyl compounds that are present. So the enolate can react with the first carbonyl compound, or it can react with the second carbonyl compound. Okay, it will react with the second carbonyl compound, and we will get 2 beta hydroxy products or beta hydroxy carbonyl products. We're going to get a product where we have R1, C double bond O, hydroxy, R1 and methyl group. And we're going to have a product where we have R1, C double bond O, hydroxy, and then R2 and R2. So we have 2 products now. Okay, so we have cut down, or we've eliminated 2 possible products here, and we brought it down to two products that we get. But we're still getting a mixture here, okay? So how do we fix that now? Can we make it better, even better? And what is the issue here? And when you think about it, the issue seems to be the fact that when we react this compound, which has the alpha hydrogen in it, with the base, we are making the enolate, but there's equilibrium, right? We don't make a lot of the enolate. That's the issue here. This reaction is not favored. You make some enolate, but there's still a lot of the carbonyl compound present. So how can we solve this issue? We can switch out the base. We can use a stronger base. what would happen under those conditions? If we convert this base, or if we use a stronger base, let's say sodium hydroxide, sodium hydride instead, when we react this with sodium hydride, sodium hydride is going to convert this carbonyl compound completely into the enolate. There's no equilibrium there, okay? And part of the reason there is because your hydride, when it deprotonates, it becomes hydrogen gas, and that just escapes. So you're able to completely convert your carbonyl compound into the enolate. And so that means after the enolate is formed, there is no more of this carbonyl compound left. So you're basically closing that pathway, or you're basically ruling out that reaction, okay, because there's no carbonyl compound left. And the only possibility for this enolate is to react with the other carbonyl compound. And it's going to react with the other carbonyl compound. And so essentially what's going to happen is, under these conditions, this will be our only product that will be formed, okay? So that's one way, or that is like the best way to run a crossed-aldol reaction, so that you can avoid the formation of multiple products by using a strong base to convert. Well, there are two things that we're doing. First, we're using only one of the carbonyl compounds, or we want only one of the carbonyl compounds to have an alpha hydrogen in it. We want the second carbonyl compound without any alpha hydrogens. So that's one thing. And secondly, we use a strong base, because if our second carbonyl compound also has alpha hydrogens, then we will still make two enolates here. We don't want that happening. So we want to use one carbonyl compound with no alpha hydrogens, and we use a strong base here. Now, again, when we say strong base here, what we want is, we want a base that's going to completely convert the carbonyl compound into the enolate. Now let's look at some examples that involve crossed-aldol condensations. So we have a ketone here, and we're reacting it with LDA, followed by the addition of benzaldehyde, and then there's a third step of water. Okay, so let's see what would happen in each of these steps. So the first step is going to convert, the LDA is going to convert the carbonyl compound into the enolate. So I'm going to work on these problems here. So the LDA is going to convert this into an enolate completely. So we will get the enolate. And now notice for this cyclopentanone, there are two alpha carbons. Both of them are identical. Only one of them, we can convert either one into the enolate. And so that's the first step here. And then in the second step, we react this with benzaldehyde. So the enolate is going to attack the carbonyl carbon of the benzaldehyde using the alpha carbon here. And that's going to give us the ketone, where we formed a double bond between the alpha carbon and the carbonyl carbon of benzaldehyde. And then the final addition of water, which is a protonation step here, that's going to convert the carbonyl compound, or this alkoxide, into the beta hydroxy alcohol. Okay, beta hydroxy carbonyl compound, beta hydroxy ketone is going to convert it into the beta hydroxy ketone. So that will be our final product after all of these steps. We can see another example here. So start with acetophenone, and we react it with sodium hydride. Sodium hydride is also a strong enough base to completely deprotonate the alpha hydrogen. So that's going to give us the enolate. And now the enolate can react with the aldehyde here. So the double bond comes down, attacks the carbonyl carbon, and the double bond is going to open up here. And it will give us a bond between the alpha carbon and the carbonyl carbon, that molecule. So there's our alpha carbon, alpha carbon, alpha carbon here, and the carbonyl carbon now becomes the beta carbon. And then finally, when we do the water workup, so that was the second step there, we basically get our product, which is a beta hydroxy ketone. So that will be our product. So those are some examples of crossed aldol condensations.